Moving raw data into a strictly ordered sequence is one of the most common requirements in computer science. To do it efficiently, we rely on a specific class of logic known as sorting algorithms. We begin with one of the most structurally simple and mathematically predictable models in this category, selection sort. The logic follows a relentless, repeating loop. The algorithm searches an unsorted space, identifies the absolute minimum value, and moves it to a protected, sorted boundary. This bar chart represents a sample dataset of 5 unsorted integers. We will use this specific array to prove exactly how the algorithm's mechanics operate. First, we'll map the pseudocode architecture, then a precise dry run. Finally, we'll derive the operational costs. Selection sort relies entirely on structural simplicity. That simplicity makes it predictable, but it introduces strict mathematical trade-offs we need to measure. This split-screen diagram maps the algorithm's control flow. The pseudocode reveals that the logic relies on a nested loop structure, dividing the work into 2 distinct roles. The outer loop acts as a boundary manager. Its specific job is to track and advance the dividing line between the sorted and unsorted portions of the array. The inner loop operates strictly as a hunter. It relentlessly scans whatever remains in the unsorted section to find the lowest possible value. Looking back at our sample array, we established the starting state. Before the first pass begins, the entire sequence is classified as the unsorted partition. This nested architecture dictates a rigid behavior. The algorithm executes an exhaustive search on every single pass, regardless of the data's initial layout. Let's execute pass 1. The algorithm points to index 0 and sets 64 as the initial candidate for the minimum value. The inner loop activates and tests the next value. 25 is smaller, so the algorithm registers it as the new minimum. The scan continues. 12 is smaller than 25. The minimum updates again. Next, it tests 22. Because 22 is larger, the condition fails, and the minimum variable remains anchored at 12. Finally, it tests 11. The variable updates one last time, securing 11 as the absolute lowest value in the array. With the entire unsorted space scanned, the algorithm executes its core operation, a direct swap, trading the absolute minimum with the first position. The outer loop advances. A rigid boundary is drawn, establishing position 0 as a newly created sorted partition. Because the inner loop checked every remaining number in the set, we have mathematical certainty that this first position is permanently solved. We move to pass 2. The sorted boundary protects the 11, meaning the algorithm only processes the unsorted side of the line. The logic repeats. It scans the remaining numbers, identifies 12 as the lowest, swaps it with 25, and advances the boundary. Pass 3. It scans the final 3 values, pulls 22 to the front, pushes 25 back, and locks the boundary again. On pass 4, an interesting condition occurs. The first candidate, 25, is actually the true minimum. The algorithm logically swaps the item with itself. The boundary moves, but no physical data relocation takes place in memory. For any array containing n elements, the process completes in exactly n-1 passes. The final element is mathematically guaranteed to be the largest. The sorted boundary operates exactly like a physical ratchet, growing by 1 element per pass, moving strictly left to right until the dataset is consumed. Now that we understand the physical movement, we need to quantify the raw mathematical cost of executing those comparisons. Look at this equation. In pass 1, evaluating an array of n elements requires exactly n-1 comparisons to find the minimum. As the n-sorted partition shrinks, the cost arithmetic progresses downward. Pass 2 takes n-2 comparisons. Pass 3 takes n-3, all the way down to a single comparison. By summing this sequence, we derive the precise, unchangeable formula for the algorithm's total comparison count, n times n-1 divided by 2. When we drop the constants to translate this into big O notation, we are left with a strict quadratic limit, n squared. This chart plots our best-case scenario. Even if we feed the algorithm an array that is perfectly sorted from the start, the complexity remains omega n squared. If we test an average mixed array or a worst-case reverse-sorted array, the nested loops still force the system to check every single remaining element. Because the comparison count is perfectly fixed by the formula, all three complexity curves trace identical paths, locking the algorithm into a firm theta n-squared performance. This exposes a critical flaw. The algorithm is blind to the data. It cannot recognize a sorted sequence or break its loop early. While the time complexity is rigid, we must also measure its space complexity, how much active memory the algorithm demands to do its job. Checking the code, we see it relies on a single temporary variable to handle the swaps. Because the extra memory requirement remains constant, selection sort operates entirely in place. Next, we test for stability. A stable sorting algorithm perfectly preserves the original relative order of duplicate elements. Look at this specific edge case array. We have two identical 50s, visually tagged A and B to track their starting positions, followed by a 20. When we execute pass 1, the absolute minimum, 20, is swapped into the first position. This action physically yanks 50A backward, permanently destroying the A-B sequence. Because the algorithm relies on long-distance swaps across the array, it inherently skips over adjacent data. That physical mechanism makes it definitively unstable. To understand its practical utility, we must contextualize selection sort against its algorithmic peers. This matrix shows how selection sort aligns with bubble sort. Both share an identical theta n-squared time complexity. But look at the physical operation costs. Selection performs vastly fewer write operations than bubble sort. However, bubble sort preserves data stability, whereas selection sort cannot. Both remain efficient, in-place solutions regarding memory. Selection sort is rarely deployed for raw speed. Its mathematical advantage appears only in restricted hardware environments, where writing data to memory is exceptionally expensive. Let's lock in the derived metrics from this analysis for quick revision. The core mechanism operates a relentless three-step loop. Find the absolute minimum, swap it to the boundary, and repeat the scan. Because of its fixed arithmetic, time complexity is locked at theta n-squared across all scenarios, while space complexity maintains a tight theta 1 footprint. It operates fully in place, but its reliance on distant swapping means it is never stable. These basic iterative loops are easy to implement, but they create a quadratic processing bottleneck that modern, massive datasets simply cannot tolerate. To sort at scale, we have to rethink the architecture entirely. In the next part, we break the barrier by introducing the divide and conquer strategy.